Well lads, I'm going to go through the 2017 higher level short questions here in this video. So for A1, the image below shows a Bluetooth mini speaker. The speaker is based on a cube with its faces cut as shown. The drawing on the right shows an incomplete axonometric projection of a similar cube using the axonometric axis method. The planes of reference are also included. The elevation and plan are shown in the required positions with lines drawn on the three visible faces. Part A, complete the axonometric projection of the cube and the given lines. So basically what we need to do is complete this intersection here. So first of all, what I'm going to do is I'm going to draw the rest of the outline of the cube. So we extend this up here, and that height stops where the top corner of the cube here hits it. So that point there. And what I can do then is I can draw that in heavy as a result, and then connect these two lines together as well. So we have the outline of the cube. First face I'm going to focus on is going to be this side here. So you can already see we have point D at the edge there, and that connects back to this point here. So same idea again for the axonometric axis. Take all our lines back parallel, and where that hits, I can now connect those 2 points together. The other one I have this line here that's on the ground connecting up to here. So basically this line here. Take those 2 points in. So once again going parallel. So you can see that line passes through that point. There it is on the ground. And on the top, it's given RATU as that line there. And we connect those two together. Next first thing we'll look at is the top. So we can see true shape there at the top. So what we need to do is just take all of our points up then. So you can see already these two are going to line up automatically. And then the back surface there, that line there at the back gives you, so that line there is going to be this line here. And then we have these two ones that cross over each other as well. So same idea again. I'll take up the two ends here. So that gives me that point there. And that point there. And the front one connects to here. And the back one connects to there. So I can see this point connects to that point. And then finally, these two connect as well. And that completes the top surface. For this side here, I need to use my axonometric view up there. So my elevation. And I'm given line CD already. So what I need to do now is take down A and B. So B is on the ground. There's point B there. And A is on the top. And that's point A there. So A actually, so line up, make sure I got that right. A connects to B, and then A passes through that top point there. So you can see there, A is that point, and it connects those two lines top there, and then back down to B down there. And obviously you have D here and C out here. That completes part A, complete the axonometric projection of the cube and the given lines. Part B, determine the true angle between the lines AB and CD. So what you need to do is, you need to see a true shape of this side of the cube here. If you see a true shape, you'll see the true angle that is made between the two lines. So you already have an edge view here. So what you need to do is looking perpendicular to that. Also as well, that's a true length. By having a true length, we can form a true shape. Which are X1, Y1. And because it's a cube, the height is going to stay the same as the width. But we just get our height anyway from there and apply it to there. And now we have true shape of this side of the actual cube. And now what we need to do is just plot the points A, B, C and D. So you take them down from our elevation to find them in plan. When you take A down, A is already given to you there. B taken down projects off there. C is actually on that line there, and D is on this line there. So we have A, B, C and D. Now I just need to take them up. C is already on that line. B, we're told, is on the ground there. A, we're told, is on the top. You can see there as well, A on the top. And D is on this line here. So we know as well our heights never change. So we can take the height of C and apply it to there. Take the height of D, which is this height here, and apply that to there. There's D and there's C, and we need to connect them together. Now we can see the true angle between the two, and there we have the dihedral angle. So simple as that. I'll just take off my page, move it down to the question below so you can see it nice and clearly, and move on to A2. So A2 tells the graphic below shows the logo for the Ladies Professional Golf Association. It contains a combination of geometric curves depicting a female golfer. The main curve is a parabola and the club shaft is a normal to the parabola. The drawing on the right shows the axis AA1, the directrix DD1 and the focus F of a similar parabola. Locate the vertex and draw a portion of the parabola. So we know from conics with a parabola that the eccentricity is equal to 1, therefore it's going to be at 45 degrees. So very simply, we can go from A1, where our directrix is our axis, we can draw our eccentricity line there. I also know that to find our vertex, we always go 45 degrees back from the focus to hit the eccentricity line and drop that line down, and that'll give us our vertex. Now to plot some points on the curve, what I'll do is I'll take a series of lines, or ordinates as they're called. That should be plenty there. And I'm going to actually now start to plot out my points. So, just like in the 2019 paper, where all of our ordinates hit the eccentricity line, we take them back to our focal line there. That one goes back to there, that one goes back to there. This one's already on the focus, so I need to worry about that one. This one goes the other way, and this one goes the other way back to hit the focal line there. We always take our compass from the focus upwards, so we rotate that back to give us a point there and there. Rotate that back to give us a point there and there. The height for here is going to stay the same. It's going to be touching off the eccentricity line, then going below. And then this one rotates back into position here and there. And then the last one, that can rotate back to give me that point there and that point there. And if you want to, you could draw one more line in between if you want to get one more point, because the distance is far enough away. But I'll just go with it the way it is. So there's all my points. And now I need to draw in my freehand curve. So there's my freehand curve drawn in for the parabola. And that completes part A. Part B, locate a point P on the curve, which is 30 millimeters from the directrix, and construct a normal to the curve at point P. So it's going to be 30 mil away. So there's a point that's 30 mil away. Now take the curve, and I'll go parallel to the directrix, because I want to make sure it's always 30 mil away. And it hits my curve at the top here. You could also take it down to the bottom if I was doing the lower half. Doesn't make a difference. I'll just stick with the top half. And that point there is going to be point P. And to find the normal, so we're not asked to draw a tangent, so we're asked to draw a normal. We join P to F, and we know from conics that our second focal point is located at infinity. So we go parallel to our axis from P, and somewhere out there is going to be our second focal point. So what we do as usual, bisect the angle in between the two. So we find our midpoint there. And very simply, from P to there, that gives us our normal then as a result. And that completes part B, locating point P and then drawing the normal to the curve at point P. Now moving on to A3. So A3 is this question here. Let's get my sheet tape down again. A3. A design for a patio fireplace based on a regular solid is shown. The drawing shows the elevation and plan of a similar solid. All faces are regular pentagons. Part A. Using the given x1, y1, draw the true length of the line of intersection between faces A and B, and hence determine the dihedral angle between the two faces. So the common line between A and B is this line here. So we want to find the true length of that line there. So in plan, that's going to be this line here. And here is A and here's surface B. So what I'm going to do is turn them into a triangular surface. Just like what we're used to in other questions, where we have one triangle there for representing A and one triangle here representing B. So instead of using the whole pentagon, we just divide into a triangle there. And we want to find the true angle between those two planes there. There's the line of intersection, and there's the height of it. So we're given the x1, y1, we're told to look in this side here to see the true length. So what we need to do is, we need to take out all these points here. These 2 points, remember we go 2 views back for an auxiliary. So 1 view back, 2 views back. This point here is on the ground there. And this point here is on the ground there. So both those heights are going to mark there on the ground. The next one, this bottom corner here, that's on the ground there. So that gives us that line there. And now the actual line that we're looking for, we take our height here and we apply it here. And now we actually have our true length there. So this line here, that line, and there it is, an auxiliary is a true length. And to see it as a point view, we look in parallel to that there with our x2, y2 perpendicular to it. So draw that there. And then we extend out our 2 points on the ground of the triangles, so that point there, and that point there. And let's draw my x2, y2 in heavy. And now what I'm looking to do is go 2 views back again to see it as excuse me, see it as an edge view so I can see the true angle. 1 view back there, 2 views back going into my plan. So we want to see this line as a point. And just to prove that we are measuring the right view, we can see the distance back to there is the exact same as the distance back to there. So there's that point there, and then the 2 on the ground, that point there, follow that up, and then we stretch our compass out to that point there. And that gives us our dihedral angle there. Next part, determine the center point of face B in plan and draw the projections of a sphere which rests on the horizontal plane is also in tangential contact with the center point of face B. So basically there's going to be there's going to be a sphere sitting inside here. It's going to be touching off surface B there, which is obviously going to be on this surface here as well in plan. And we have to draw it. We have to first of all find the center point of face B so we can see where the sphere is going to go. So face B is this outline here. So the first thing we need to do is bisect this line here to find the center point of it, because both lines are parallel. Bisecting it, we find the midpoint of the actual length of that line. So we find the halfway point up so we can connect to the opposite corner as a result, which will give us the center. So bisecting it. So there's the halfway point. And I'll join that to the opposite corner there. And where that crosses gives us the center of that face there. So we're told it's going to be the center point of face B. That line there, if you imagine just a regular hexagon, if I just draw one out here, just lightly, just like that there. That line there going down through it is basically equivalent to like this line here. And then if I find the center point, I can get that there, passing through it. And that gives me center of face B then as a result. So that's what basically I was trying to figure out there. Now I need to find that in my elevation, so I do the same thing again. Bisect the line because they're both parallel. That line there is that one there. They're both parallel, and when I bisect them in both views, they're going to give me the midpoint. Join those two together. And once again, I connect it to this face here. So I connect it to that face there as well. There's my actual center point. I can take that up now. And there's the center of the face there. So there's the point of contact that's going to occur with the face B. Now the next thing I need to do is draw an edge view. If I draw an edge view, looking in this way, I can see the actual side of the sphere because I'm not given it. So we're told it's resting against B there, so I want to make this line appear as a point view so I can see it as an edge. Draw my X and Y one. And once again, getting my heights from my elevation. So I take that height there, which is 26 mil, and I apply it to there. 26 mil, join it back. And now what I need to do is I need to bisect the angle to find the center point. Just give me 1 second to get my compass. So bisecting the angle. So somewhere along that line is the center point. We already have the point of contact there. So what we can do very simply is we can take that up and go perpendicular to it there, like a normal. That gives us the center point of the sphere. And then all we need to do is take that as a radius there, draw our sphere. That would fit in there, keeping that radius, following it back there, draw our sphere in our plan. And then finally, drawing it in our elevation. So there's the center point. Take the height up. And there we have it in all three views. And the last thing I can just simply do is draw that heavy there and dash that there. So it's been blocked. And that completes part 3, so A3. And the last one, A4. So for A4, lads, what I'm going to do is I'm going to send you a link showing a SolidWorks model of how that question looks. So basically this one here. And the model basically to explain to you how to solve part C. It looks a lot easier to follow. So I'll send you that for that one there. And if you're still unsure about how to complete it from the video, I will actually do that as a separate video then as a result. So hopefully that helped.